This next little video is going to be on two heat transfer processes. And so heat transfer concerns not just the phase or the temperature of an object, but how that changes over time. And conduction and convection are similar because they both involve uh, mass actually being next to each other. So in order for conduction and convection to happen, you have to have some molecules that can bang into each other and transfer some of their energy.
So conduction is the one we're perhaps more familiar with. And when we talked about thermal equilibrium, we were really talking in terms of conduction. So when you have a higher temperature area, like over here, your molecules are moving faster, have more kinetic energy, and they might collide with the molecules from a lower energy part of your system, and they're going to transfer momentum. So now our blue one is moving faster than our red one, and they're going to consistently transfer momentum from the high temperature area to the low temperature area, and eventually that's going to spread and throughout the whole system and create equilibrium. That process is called conduction. That is the movement of thermal energy by collisions between molecular particles. This can occur in a solid, obviously, but it can also occur in a liquid or a gas. In a solid, the picture here becomes a little misleading. In a solid, you have the lattices, right? But lattices of molecules, but in the high temperature, those are jostling at a higher rate than they are at the low temperature, and that jostling creates the same sort of collisions and energy transfer into the lower temperature area. Okay, so for each of the modes of heat transfer we're going to talk about, we're going to have a rate equation. And what that rate equation does is it tells you how quickly thermal energy is moving from one body to another body. So we're going to imagine a situation over here where we have one temperature bank that stays at the temperature T2 and another material over here that stays at temperature T1. And we have an intervening material, this bar here. And we're wondering how fast is heat going to move from here over there? How much heat transfer are you going to get? And so it's going to depend on four factors. One is the area of contact, right? How thick is this, or how big is this cross-sectional area? How much surface is connecting T1 and T2, right? So the bigger that is, the more heat transfer you're going to get. You might think of this in terms of a pipe, right? If you have a big pipe, you're going to get more flow of water. And if you have a big area here, you're going to get a bigger flow of heat. The thickness of the material matters too, right? The thickness from here to here. The longer that distance d is, the less heat transfer you're going to get, right? So essentially, if your T1 is close to your T2, it's going to move heat quickly. If they're far away, less quickly. The size of the temperature makes a big difference. So if T2 is much different than T1, you'll get a big rate of heat transfer. And then finally, the thermal conductivity K matters a lot. What does that mean? It means how good is this material at moving heat from one place to another. So something like aluminum is very good at that. If you heat one end of an aluminum rod, the other end is going to get hot very quickly. But there are other materials that are made to be insulative, like insulation, that you might have, it might take a very long time for heat to move across that material. And that's represented by this thermal conductivity K. So if we take these four factors and we put them in an equation, we get what's known as Fourier's law. And that tells us that Q, that the thermal heat transfer per time, right? So that's watts, that power, how much heat transfer is moved in a given amount of time, has to do with K, our thermal conductivity, A, our area of contact, or our cross-sectional area, the difference between T1 and T2, and then D. D is the one thing that's going to slow that heat transfer. So if this is our rate equation for conduction, what do we do if we have a wall like this over here and we want to make sure that we don't lose a lot of heat in winter? Well, you're not going to be able to control T1, T2 very much, although you can turn down your thermostat, right? So if we turn down your thermostat, you're going to lose less heat because there's going to be less of a difference between the inside temperature and the outside temperature. We can't change A because that's just the size of your house, right? The size of the outside walls. So you could build a smaller house and you'd have a smaller area and then you'd lose less heat. But we can change K, right? We can change the material of those walls, and that's why we put insulation in them. And we can change the thickness of the walls, right? We could make our walls particularly thick. So that ratio D over K is called an R factor, and basically it offers resistance to heat transfer, right? So if you're thinking about putting insulation and you go to the hardware store, you'll see insulations rated with an R factor, and basically that's an expression of this ratio, telling you how good it's going to be at keeping heat from moving from one side of your wall to the other side. All right, so that's conduction. Convection combines conduction with the advection of fluid, that is the bulk movement of fluid. So you take a furnace like this here. The furnace here is going to immediately heat the air around it by conduction, right? Well, that air is going to become lighter because it's hot and it's going to start moving. So the air is going to get really hot, but then it's going to actually physically move through the room, and that's your advection, and that's what makes this a convective heat transfer. And this can be much more effective than conduction. If you didn't have any movement of fluid in a room like this, it would take a long time for that heat energy from this to get over to the far corner of the room. But convection makes that happen more quickly. And over here we can see some examples of convection at work. Like if you have a circuit board that you need to cool down, you might blow air across it, okay, because that's going to pull heat energy from your circuit board. Boiling is a form of convection, right? So as you start to heat water on the bottom, the water's actually going to start circulating in there, and that's going to help your heat transfer into the water. And here's when you see condensation, we see a similar thing. So you might have cold water going through a pipe, and it's going to pull moisture out of the air, and then that moisture is going to flow off that pipe, and that's your convection too. So convection involves both conduction and fluid flow in one process. It's harder to come up with a good rate equation for convection. This is the best we can do, where we have a difference in temperature between two surfaces. We have an area of contact, but then we have what's called a heat transfer coefficient, H. And that has to be determined experimentally, and it varies a lot. So you can see over here, you might have an H that has a value as low as 10, but you might have, if you're really trying to move heat, and there's a lot of movement of fluid, you might have one that's in the 10,000s. So again, what does this tell you? It tells you with these given conditions, how much heat transfer is going to be transferred per unit time.